Cray decided to productize the Knights Landing processor in our supercomputers because it meets an important customer need. We have a diverse set of customers. We've got government customers, people in all areas of science, industrial customers, enterprise customers, and with that diversity of customers comes a diversity of application needs. Some applications work better with multi-core CPUs that have very large memories, but others work better with the new Xeon Phi many-core processors that have very high memory bandwidth and high compute peak. The new Knights Landing Xeon Phi processor is a significant advancement over the previous generation Knights Corner coprocessor. First and foremost, it's self-hosted and self-booting. This provides an easier programming model and allows you to build more cost-effective systems. Secondarily, it has significantly higher performance than the previous generation. It has 16 gigabytes of on-package memory with extremely high memory bandwidth, and we found that very high memory bandwidth is a key contributor to high compute performance. It also has more cores. The version that we're using uses 64 to 68 cores. They have wider vector units. They've got more threads per core. This results in a single processor with over 3 teraflops of performance and over 250 threads per socket, which help you soak up that high memory bandwidth. Cray's adaptive supercomputing strategy supports diverse processor technologies in a single system. Many of our customers historically have had systems with mixed processor types, and this is no exception with the new Knights Landing systems that we're shipping this summer. Those systems have large partitions of Xeon multi-core processors and Xeon Phi many-core processors. A homogeneous system allows you to run a single capability or hero job across the entire system. It can be good for getting great benchmark numbers, but a heterogeneous system is often better for running a diverse set of applications, where you can match each application to the right processor type and optimize the overall performance of your workflow. So let's take a look at how we've implemented the new Knights Landing processor in the Cray XE compute blades. Here you can see two different compute blades. They actually have an identical form factor, and they have an identical base blade with the Cray Aries high-performance network chip on it. Each Aries network chip has 4 integrated NICs, or network interface cores, to connect to 4 local compute nodes. On your left, we can see the Xeon multi-core compute nodes. Each of those is a dual-socket Xeon node. Each of those sockets has 4 memory DIMMs, 4 memory channels, so we have a total of 8 memory DIMMs per Xeon compute node. On your right, we have the Knights Landing blade. Again, the same physical blade, but we have a different daughter card on this blade, and this daughter card has single socket Knights Landing compute nodes. So there are a total of 4 compute nodes, 4 sockets on this blade. Each one of those sockets has 6 external memory DIMMs for the large capacity memory, and then of course internal to the Knights Landing processor, we've got a very high bandwidth on-package memory system. So we have this hierarchical memory system. Each of those processors also is over 3 teraflops of performance, and so when you have 4 of those on a blade and we have 48 blades in a cabinet, you can have up to in excess of 575 teraflops of Knights Landing performance in a single Cray XE cabinet. The blades are the same form factor as I mentioned, so they're interchangeable, and you can have any number of Xeon compute blades and Knights Landing compute blades in the same system.